This is the AP Statistics Chapter 12 review. A class performed an experiment to investigate this question. Students randomly assigned 14 helicopters to each of 5 different drop heights: 152 centimeters, 203 centimeters, 254, 307, and 442 centimeters. Teams of these students released the 70 helicopters in the predetermined random order and measured the flight times in seconds. The class used Minitab to carry out a least squares regression analysis of these data. What is the equation of the least squares regression line for this data, and define any variables used? So when you go to write your least squares regression line, you are going to look at the coefficients. Now, we write our equation in the form of y hat is equal to a plus bx, where a is your constant. So if we look at our constant, we have our constant value plus our slope is the value for our drop height times x. Since we used x and y, we need to define our variables. So x represents the drop height and y represents the flight time. Now you can also remember, you can write this as flight time, the expected flight time is equal to, and then for x you can write drop height instead, so you can define the variables in the equation, or you can just use your x and your y. Interpret each of the following in context. So our slope in context, we've already found the value for our slope, but now we need to tell what that represents. So the slope tells us for each 1 centimeter increase in the drop height, because our slope is talking about the drop height, we expect 0.0057244 seconds added to the flight time on average. Next, we need to talk about the y-intercept in context. So this is our y-intercept. The y-intercept tells you when the x value is 0. So in context, the y-intercept for this problem has no statistical meaning. If a helicopter is dropped from a height of 0 centimeters, the flight time would be negative 0.03761 seconds. And it has no statistical meaning because we can't drop a helicopter from 0 centimeters off the ground. Next, we're going to talk about the S value. And we can see from our table our S value. Remember, the S value tells you the typical predicted flight time will vary from the actual flight time by about 0.168181 seconds. So it's telling you on average how far off your prediction is for your Y value. Next, we're going to look at the standard error of the slope. So remember, to find the standard errors, we look at our standard error coefficient, and we are looking for the one for our slope. So that means this is our standard error of our slope, but we need to put that into context. So this tells us if we repeated this experiment many times, the estimated slope will vary from the population slope to predict the flight time from the height of the drop by an average of 0.0002018. So this is how far off our slope is for each regression line on average. Then we're going to look at the R squared. So there's an R squared and there's an R squared adjusted. We are going to use just the R squared. And remember, the R squared tells you about the variability. So about 92.2% of the variability in flight time is explained by the linear relationship with the height of the drop. Assume that the conditions for performing inference about the slope beta of the true regression line are met. Do the data provide convincing evidence of a linear relationship between dose and weight gain in the following problem? This one should be not dose and weight gain. It should be between drop height and flight time. And we're going to carry out a significance test at an alpha equals 0.05 significance level. So this is going to be a 4-step problem. We're going to start with our state. Remember, in your state, you need to give your null hypothesis, the alternative hypothesis, you need to define your parameter, and you need to give your alpha level. So we want to perform a test of the null hypothesis is that beta equals 0, which means there's no linear relationship. And the alternative is beta does not equal 0, where beta is the true slope of the population regression line relating drop height to flight time when the alpha level is 0.05. Next is your plan. This is when you say what method you're going to use, and you're going to check your conditions here if you need to. So they already told us in the problem that our conditions for performing the inference have already been met. So we just need to state that they have already met those conditions, and then state what method that we are going to use. So we will do a t-test for beta. Next is the do part of this. This is when we actually do the calculations. They already give you the calculations. You just need to state how you would find it. Now remember, to find the degrees of freedom in this case, it's going to be n minus 2, where n is the number of trials, and they tell you that you dropped 70 helicopters. So we're going to do 70 minus 2 gives us 68. And if you look at your output, we are talking about the slope, which is this line here. It's not the constant, which is the y-intercept. It is the slope. And it tells us our t-value is 28.37, and our p-value is 0.000. So the last thing we need to do is we need to write our conclusion. And since the p-value is less than 0.05, we reject the null hypothesis and conclude that there is convincing evidence of a linear relationship between the drop height and the flight time for the helicopters. Now we need to construct and interpret a 95% confidence interval for the slope parameter. Again, this would be a 4-step problem. We're going to start with our state, and that tells us what we need to do for this problem. So we want to construct a 95% confidence interval for beta. Next is our plan. This is where you say what method you're going to use and check your condition. So since it is stated that the conditions are assumed to be met, we will construct a t-interval for the slope beta. Next is when you do the do process. Now remember, when you are finding the interval, you are going to do b plus or minus the t star times se sub b. We need to find our degrees of freedom so we can find our t star value. And again, it's just n minus 2, so we're left with 68. Now, if you go to table B to find your t star value, there is no line for degrees of freedom of 68, so you have to go to the next smallest number, which in this case will be 60. And if you go across the row for 60 until you get to the 95% confidence interval, you will see that t star will equal 2.000. Now, we need to use our b value, which is the coefficient for the drop height. We need our t star, which we found from the table, and we need our se sub b. So this is the se for the drop height because it's the slope. And if we put that into our calculator, if we plug this part in first to see what we're going to add or subtract, remember you are going to subtract first to get the first number, add to get the second number, and this will give us our interval. Then we just need to write our conclusion. So we are 95% confident that the interval from 0.005328 to 0.006218 captures the true slope of the population regression line for predicting flight time from the drop height. Imagine that you have been put in charge of organizing a fish tournament in which prizes will be given for the heaviest Atlantic Ocean rockfish caught. You know that many of the fish caught during the tournament will be measured and released. You are also aware that using delicate scales to try to weigh a fish that is flopping around in a moving boat will probably not yield very accurate results. It would be much easier to measure the length of the fish while on the boat. What you need is a way to convert the length of the fish to its weight. You contact a nearby marine research laboratory and they provide reference data on the length in centimeters and weight in grams for Atlantic Ocean rockfish of several sizes. Explain why a linear model may not be appropriate for this case. So if you look at this data, the graph of this data, you can easily see that there is a curved line to this data. So there is a clear curvature evident in our scatter plot, so a linear model would not be appropriate. you decide to cube the length of the fish. After transforming the data, a least squares regression analysis is performed. Some computer output and a residual plot for the possible regression model follow. So here is our new scatter plot. What they did was they took the length or the x value and they cubed them and then plotted it against the weight. And as you can see, we now have a much more linear model. The next is the residual of our plot. So it's length cubed is our x value against the residuals, and it gives us our computer output. So we need to give the equation of the least squares regression line and be sure to define any variables. Remember, you can define the variables directly in the equation itself, or you can put x and y and then define the variables later, and you are going to look under the column for coefficients. So if we do this, we are going to get that our y hat is equal to 4.066 plus our slope of 0.0146774 times x cubed. And remember, we do have to have the x cubed because we did take the length and we cubed it, where x represents the length of the fish in centimeters and y represents the weight of the fish in grams. Now we need to use that model that we just had to predict the weight of the fish with a length of 33.5 centimeters, and we need to show our work. So we are taking that equation we just had and we're just plugging it in. So our length is our x value, so we're going to plug in 33.5 into our x. You would cube that and then multiply, and this would give us our predicted weight would be 555.87 grams. A scatter plot of the natural log or log base E, which we write as ln, of the number of transistors on a computer chip versus year since 1970 is shown. The mini-tab output for the linear regression analysis of the transform data is shown below. Give the equation of the least squares regression line. Be sure to define any variables that you use. Again, you can put the variables directly in, the definition of the variables in, or you can write this as y and x and then define the variables separately. We are looking under the coefficients, and this should be the ln of y hat is equal to 7.0647, because that's our constant, plus our slope, which is 0.036583x, where x represents the number of years since 1970, and y represents the number of transistors on a computer chip. Next, we need to use this model from Part A to predict the number of transistors on an Intel computer chip in 2020. So we're going to take the number of years since 1970 to 2020, which is 50 years, and we are going to put that into our x value. Now, if we take everything on the right side and go ahead and calculate that, that's going to give us the ln of y is equal to 25.3562. And we need to remember that ln is log base e. So if we want to write this as an exponential, we can write this as y is equal to e, because it's log base e, raised to what the answer is of 25.3562. And that's going to give us that our y hat, our predicted number of transistors, is 1.028 times 10 to the 11th power.